partial. So if you watched my videos, you saw that there were these guidelines here. So if you have an improper rational function, that's where the degree of the numerator is equal to or greater than the degree of the denominator, you have to do polynomial long division first, and then you can tackle the PFD on whatever's left. If there's a quotient that you can do PFD, partial fraction decomp on. And then you have to be good at factoring. You have to be really good at factoring polynomials in this section. So I'm hoping that you're polynomial experts since you're graduates of algebra and pre-calculus, but we'll find out. And then if you have repeated factors, that's going to be an issue because for every repeated factor, you have to have an additional partial fraction and so on. And then the issue for these partial fractions is you are in charge of finding the unknowns, and that's half the battle. Like I take away 50% of your money, your points, if you fail to basically get the correct unknowns, because that's really like the key. And by the way, I want to mention something about the quiz, which has a lot of PFD in it. I think because this is such a hard quiz, instead of 100 points, I'm going to make it 200 points. So it's going to be worth more points. So that's going to entice you, hopefully, to do well, right? So you don't want to mess that one up. Sure, you can drop your 3 lowest quiz scores, but this is where a lot of the pedal to the metal is going to hit, okay? So back to hand-to-hand combat here. So I'm going to skip that one. Let's skip all the way over to letter D. And what about these other examples? Well, you go do it. Go look at my videos. I did all of these in detail for you, every single one. So let's look at letter D. This one's a hard one. Do you think I'm going to put a hard one on the quiz? Oh, I got 8 of them just for you. And yes, one of them is going to involve polynomial long division. Some of you still need to work on that. Some of you are getting a lot better. Keep up, keep getting better. So look at this mess. Oh my goodness. Do we need to do polynomial long division on this? Yes or no?
No.
Good. Why not?
Just because of the degree of denominator is higher than numerator.
Good. That is exactly right. Congratulations. You have it right, John. Kudos to you. Yeah, so no polynomial long division. Instead, what do we do next? What's the next step? I'll give you a hint. You have to do something to the denominator. Anybody watch the videos? Yeah, you got to factor this. Well, how do I do that? Oh, carefully. One thing I'm going to notice, it's a 3rd degree polynomial. So it does have a common factor of x. So if I pull out a common factor of x, then the other factor looks like x squared plus 2x plus 1. Is that completely factored over the set of integers? Or am I done? Factoring, that is.
You need to factor once more.
Okay, good. How does this factor?
X plus 1 squared.
Good. So what do we have here? That denominator has a linear factor, just x. And then this x plus 1 is getting repeated because it's squared. So this is what's known as a repeated linear factor. And you have to do something extra for anything that gets repeated for as many times as it gets repeated. So the algebra that you're going to do, and there's a lot of it, so like the scratch that I need to do, is the original quotient, I copy it down, and the denominator, I put the factored version down. And then I decompose it into partial fractions, and that's why they call it partial fraction decomposition. So for this first factor, just the x, the partial fraction will just be some unknown a divided by x. Plus, the next partial fraction is going to be b over x plus 1. And since x plus 1 is repeated, you're going to have another partial where the denominator will be x plus 1 squared. Now your job is get those unknowns, a, b, and c, and they're just pure numbers. And you can't guess. You can't go, well, I think a is 2 and b is 17 and c is 11 halves. You can't do that, although that might be right. But you have to show me all the work, and it's a lot of work. Now I'm going to show you the Professor Rasky way to do this, And I encourage you to do it my way because I show you the easier way to do this. There are other approaches. One approach is to leave everything as fractions and equate the numerators. I don't like that approach. I prefer killing off all the fractions and then just examining the equation that's left. It's a little bit less messy. Now, back to talking about different approaches. There's some of you who, when I look at your handwritten work, some of you still aren't showing me enough appropriate work, or it's a hot mess where I can't even read it. So then I just take away a lot of points. Like, I can't read this, and you go down in points. And the other thing is I'm seeing some people do stuff that, again, is not the conventional approach to doing you know, the matters at hand. Like some of you are doing W substitution, which is unnecessary, and just some other wild stuff. So please, I encourage you to review the graded files that I upload back to you with my handwriting on it and my comments on there about, you know, like, please don't do this and some other things like that, so that you can maximize your points for the future. Okay? So please read that. So this is the approach I prefer. You kill off all the fractions. Well, how? Well, you've got this big old equation that's got fractions all over the place. It's really messy looking right now. So what is the LCD, the lowest common denominator of all the fractions that you see in this entire equation? Because you're going to multiply both sides by this LCD. Does anybody know what it is?
The denominator?
Which denominator? Because I got all these different fractions.
Sorry, the one on the left.
Yes, the one on the left, right. His denominator happens to be the LCD. So if you multiply both sides of the equation by that LCD, you will clear fractions. And that's the goal of the Professor Rasky approach. I didn't make this up. I got it from my calculus books I learned from. So after simplifying everything, the left-hand side is just the numerator. And then when you distribute this LCD over the sum and reduce to lowest terms, the first term, only the x's cancel, so you'll have a times the quantity x plus 1 squared. The second term, one of the x plus 1 factors cancel, but nothing else does. And the last term is c times x, and then you're done. Now this equation here has a name, and I'm going to call it the basic equation from now on. And if you have the basic equation somewhere on your paper, I'll give you at least 1 point of partial credit because I'll be so happy, because that says something. Now what? Use the basic equation to help you get your unknowns, A, B, and C. How? Very carefully. You got to think. Well, the first thing I'm going to do is I'm going to go, what can I substitute for x that would kill off all the terms except for 1? And it turns out, since the b and the c terms have an x in there, if we let x equal 0 everywhere and substitute a 0 in place of x in this entire equation, the second and third terms on the right will just go to 0 because of, you know, plugging in x equals 0, they go away. And we can find one of our unknowns, a. That's good news. So on the left, we just end up with 6, and then here we have a times 1, and then you solve for a, well, it already is, and I just have a is equal to 6. Yeah? Solve for a, and you get a is 6. Okay, that was too easy. Are they always that easy to get? No. Sometimes your unknowns are pretty difficult to get. You have to work hard. So what's another obvious value you can substitute in for x that would kill off 2 of the unknowns but keep one of them standing? And I hope you can see that if you let x equal -1 in this basic equation, so I'm going to have to substitute a -1 everywhere I see an x. So for this first term, I hope you can appreciate that -1 plus 1, that's going to go to 0. So he's out. Come on, baby, get rid of it. And then the next term is also going to go to 0. And then the last term, since you're letting x equal -1, you have c times -1. So on the left here, you have 5 plus -20 plus 6 is equal to -c, and you're just trying to solve this for c. So I think this side is -9 is equal to -c, and then multiply both sides by -1. And voila, I got another one of my unknowns. Yay, 2 out of 3. Now go get the last guy. Now this one is not that hard to get, except going back to your basic equation, because that's what you always want to go back to. There's no other values of x that I could substitute that will kill off the other unknowns. So you're going to have to think mathematically and algebraically. How about if we pick a value of x that we haven't substituted yet, something easy like 1, and we already have a and c. So if we substitute, say, x equals 1 into our basic equation and plug in 6 in place of a and 9 in place of c, the only unknown in the whole thing will be b, and that's the last guy we have to figure out. So my last attempt here to get my last unknown, let x equal 1, a equals 6 because he is, and c equals 9, and you're using all this to get the b. So when you do all these substitutions into your basic equation, and it is kind of a nightmare, and if you make one wrong move, like you have a negative accidentally stuck somewhere, it's going to be a nightmare. So you have to be very good at keeping nice, neat work so somebody can read it when they're trying to grade it. That would be me. And some of you don't like showing me all your intermediate steps. Like, well, I do it in my head. No. My internet is unstable, so if I bomb out, be patient. I'll try to reboot my internet, but it looks like it may conk out today. I don't know what to say. Bad news. Okay, so doing the algebra on the left, we'll have 31 is equal to 6 times 2 squared plus b times 2 plus 9. So if you are trying to get your b, and that's the goal, finally solving for b, I get b is -1. Now folks, these are nice numbers, 6, 9, and -1. When you do one of these PFD problems, let me just warn you, a lot of times the A, B, C, or whatever your unknowns are, you might get wacky numbers. They might not be nice integers. You might get like -5/2, or something wacky like 35/11ths or something. And that's possible. So be ready for it. Don't always think that, oh, if I did it wrong if I didn't get a nice integer. And it could be you did it wrong because you had some arithmetic error somewhere. But it's entirely possible to have really yucky numbers for your unknowns. So be ready. So now what? You substitute your unknowns, your A, B, and C, into your partials, because that's what you're going to end up integrating. So we're going to actually integrate 6 over x plus b, that was -1 over x plus 1, plus c, which we got as a 9, all over his denominator, which was the quantity x plus 1 squared. And then take the integral rather of these 3 terms. Now the first term is easy because it's just the log rule, and you don't even need u sub. That's just going to be 6 ln absolute value of x, easy peasy. The next thing is the log rule, but you are going to need u substitution, where u is x plus 1 and du is just dx. So that one is a little extra, so you'll have the minus there, and then that's going to be ln absolute value of x plus 1. Now, how about this last term? Is that using the log rule? Does anybody know? I'll open it up.
No.
Okay, so does anybody want to have a guess at what kind of rule we use?
And we also did the u substitution as well
For which one?
for 9 over x plus 1 squared.
We are going to use u sub, but I'm asking you which rule we use. U sub is not a rule. Let me give you some
Power?
choices. Log rule, power rule, sine rule, cosine rule, arctan rule, exponential rule. Do you see that these are some of the rules?
Yeah, that's a
Power.
power.
Power rule is correct. Thank you. Power rule on that one with u sub. So who's my u and who's my du then?
X plus 1 is your u,
Mm-hmm.
and then dx is your du.
Good. So really, here's some side work over here. Don't say this whole thing equals. Like some of you on your quiz the other day, when you were doing your IBP, you had like UV minus integral V du, and when you were just trying to integrate this little guy, you would go, oh, well, that equals blah, 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 like this. I'm just making a mess here. And I got really pissed when I see an equals there, because this whole entire left-hand side is not equal to just the integral of that little dude there. So I start taking a little points off here and there for sloppy notation. And I know some of you probably think I'm very anally retentive, and the answer to that is thank you for asking. Yes, I am. And I'm just training you to be a good engineer, a good mathematician, good computer scientist, good physicist, a good chemist, or whatever it is you're studying for, because you too have to be very detailed and careful about good notation and also good vocabulary. I'm a big fan of, if you know how to speak about something, that means you know it. Okay, so the power rule, so my side work is, yeah, I have a 9 there, but I have 1 over u squared du, but that's the same as 9 times the integral of u to the negative 2. And now I can use my power rule. That's going to be 9 u to the negative 1 divide out by negative 1. But then that's going to be negative 9 over u to the positive 1. So here I'm going to have minus 9 over u to the positive 1, but u is just x plus 1. And of course, plus c. Now, you may notice if you're doing some MyMathLab stuff, that MyMathLab will probably accept this as your final answer. But if you don't put anything and then you're looking later on at what MyMathLab answers are, there's another answer that MyMathLab will totally accept. And I want you to be aware of it, because I may dock you points if you don't go the extra mile. So the extra mile is, can you condense these two logarithms into one single log using some of your knowledge of algebra? And hopefully the answer is yes. So first, this 6 becomes a power, and I have ln x to the 6 minus ln absolute value of x plus 1. And then if you recall, when you have a difference of logs, you can combine that into one big old log, x to the 6 over x plus 1. And technically I probably should keep my my absolute value on my not on x to the 6, because that's guaranteed to be positive, but on the denominator. And then this guy is not a log, so he still stays the same. And there's my final answer. Kind of a mess, but there you go. So I'd make it look pretty that way. Okay, any questions on that?
I do got a question, Professor.
Sure.
So for getting C and then you let x equals to 1, is there like possible to if you also pick like any numbers and then you still get the same answer?
Yes, absolutely, Alec, but I prefer if you keep your x to something easy peasy.
Oh, okay. So you
Like if you wanted to, Alec, if you're like you want to take a risk, then I would say, hey, go ahead and let x equal 57, and a is still 6 and c is still 9. You with me?
yeah, I did that too. Like
Why would you want to pick such a horrific number like 57 unless you like working with really large numbers and substituting? So I just picked a value of x that I hadn't used up already, but if you don't like mine, certainly as long as you don't pick ones that you already used already, because you know those aren't going to get you anywhere. Like I don't use up x equals 0 and x equals negative 1 up again. Right, Alec?
no, I'm John.
Yeah.
Yeah.
I picked x equals 1, it's an or you could have done x equals 2 or something that's a low number so I don't get into too many yuckiness.
Oh, okay. No, it's like
yeah,
like,
so you still, so Jonathan in the chat box, yes, you plug in A and C, but in order to get your B, you still have X's in the mix. So you also have to substitute something in there for X also. You're not exempt from that.
all right. Okay,
Yeah, you don't have a choice. Like, this is why when I give these partial fraction decomp problems, which is heavy on the algebra, there's not much calculus. Like, do you get this entire freaking problem here? Look at this mess here. This entire problem, we didn't actually use the calculus till the bitter end. when we actually had to do some integration down here. This is the calculus part right here. Everything else is heavy, heavy algebra. And if you are a little weak on the algebra, this section is going to be a butt kicker. Now, for those of you who are like, wow, this seems like, you know, a really good way to torture young calculus students, is there any reason why we have to learn this crap? And the answer to that is absolutely you have to learn this crap, especially if you're going to take differential equations. And electrical engineers and physicists all have to take differential equations. And you might have to, like if you're another major, like I think if you're going to UC and you're a mechanical engineer, I think you also have to take 50Q, differential equations, Math 253. And they're going to have partial fraction decomp all over the wazooby in like your last 3 weeks of class. And if you can't do it, oh my God, you are going to be in so much pain. It's going to be awful. And prepare to just flunk the class. Okay? So just so you know, it's going to come back and you will see it again. And I'm teaching you all of my tricks. That's why I have so many examples. Like, I'm not the kind of person where, well, I'll just show you like a couple, 2, 3 examples for partial fraction decomp and let's move on. One of the reasons why I made 9 videos for you is because you need to experience every possible flavor there is, and you'll thank me. And yes, every possible flavor is going to be on my quiz this weekend. Oh, yeah! Because I care.
I have a question.
You got it.
To get the basic equation, do we have to like show you the steps, or I can
Yes.
say multiply by L?
I want to see the partial fractions somewhere on your paper. Like if all of a sudden magically you went from here to the basic equation magically without any intermediate steps, I'm not even going to grade your paper. 0 points, like for 0. Why? Because I don't get how you got there.
Okay.
And I'm not going to be nice about it. Like you show me all your intermediate steps like I have.
No, what I meant is like instead of like multiplying the whole denominator on both sides, I just say multiply by LCD. Or
Okay, yeah, you can do that as long as we're clear on what the LCD is.
can I just label the LCD and just say multiply by?
Yeah, like if you go, okay, this is the LCD, and I'm going to multiply both sides and get my basic equation. Boom. I'm okay with that.
That's what I meant.
Yeah, no, I thought you meant I'm going to go from the original integral to, boom, the basic equation. Just magic. And I'm going to go, whoa, I want to see the partial fractions that you denoted so we all know that we're clear on what those partial fractions were. Does that help?
No, just to save time. Yeah.
Okay, yeah. All right. So this is kind of what I'm looking for, folks. And so for one problem on the quiz this week, and I want to see all of these steps. See all this mess here? I want to see it. Now, while we're talking about messes. Okay, so let's do another problem that's a little harder. This one called quadratic factors. So when you're factoring your denominator, you're not factoring it completely over the set of complex numbers. That's a different kind of type of factoring, and a lot of times in pre-calc, and I've taught pre-calc many times, they often ask you to factor a polynomial over the set of complex numbers. But we're not going to be in a set of complex numbers here. We're going to stick to factoring over the set of integers. So what you have to know is that a sum of squares, and this right here is a sum of squares, is not factorable over the set of integers. So if I see you factoring a sum of squares, I am going to not even grade the rest of your paper, or at least that problem, because you missed the boat. Now, a difference of squares, yes, of course, absolutely. Difference of squares. Please factor a difference of squares. Sum of squares is not factorable, so leave it alone. Now, this right here you can factor, because you could factor out a common factor of x, and then you get x and x minus 1. And these are known as linear factors. And this guy here is called, and yes, it's important for you to know the vocabulary, repeat after me, irreducible quadratic factor. And I'm not kidding you, I want the whole class to join in. So what am I saying here? Let's see, I'm going to get into gallery mode here. Okay, everybody in the room, irreducible quadratic factor. On three. 1, 2, 3.
Irreducible quadratic factor.
Quadratic factor. Okay, that was a little weak. Let's try one more time.
Irreducible.
Irreducible quadratic
Quadratic
factor.
factor. Right on. Okay, that's better. All right. I'm better with that. Know how to say this stuff, people. Now what? Well, irreducible quadratic factors have a little bit different look to their partial fractions. So what am I saying? I'm saying my original integrand. So here's the scratch work. I want to see it.
Can you go back to your screen?
Oh yeah, did I stop sharing?
Yeah.
Sorry. Back to this. So here's my scratch work. I'm trying to get my basic equation right now. So I have the original integrand in factored form. The two linear factors are going to get their own little partials for themselves. And then the irreducible quadratic, he gets a very special numerator. He gets a linear factor for his numerator. Uh-oh. So his numerator, oh my God, has two unknowns, a C and a D. Yikes. And when we get the C and the D, we're going to have to use the split up trick to be able to integrate that last term. So it's going to take us some time. Okay, so I want to tee this up to let you know what's going to happen here, because it's going to be some algebra that's going to be from hell. In this problem, just to get all the unknowns near the very end, we're going to have to use the technique you learned from algebra, I'm hoping, solving a linear system that has two equations and two unknowns. And if you forgot how to do that, we're in trouble, because that algebraic technique is going to be very helpful to help get some of our unknowns. Okay, remember I told you the algebra in this section is hellacious. And so you're going to have to get that. Now, let's start first by multiplying both sides by the LCD. So this is the LCD of this entire equation. So multiply both sides by this if you want to skip that step. And what you're going to do after you do the cleanup is you'll end up with the left-hand side. It'll be just that numerator, because we're clearing fractions. And then this term, after you multiply him with this big old LCD, oh shoot, sorry. The x's cancel, but the other factors do not. And then the second term, the b, the x minus 1 cancels, but the other two factors do not. And then you're not going to like this last term. I want parentheses, and parentheses matter here. If you're missing parentheses on your uploaded work, I also dock you points for yucky notation. That whole quantity, parentheses around him, gets multiplied with x and x minus 1. Now, folks, this big old guy right here, that's worth 1 partial credit point, because this is your basic equation, and this is the equation that you're going to use in order to help you get all your unknowns. Okay, let's start off something easy first. Do you see an obvious value of x that you can substitute into this entire mess that would kill off the b and the b term and then the very last term?
0.
Good. So you're going to substitute x equals 0 in this entire basic equation, and that is going to kill off the last two terms because they both have an x term in it, so they'll be gone. Like, yay, they're gone. And the good news is you can get your A. So you'll be able to pick him up. And be careful here because you still have a little bit of algebra left to do. And then when you solve for A, I get, after dividing both sides by -4, A equals +2. So I always put a circle on that and then save it for later. Why? Because later on, he's going to be the numerator for my x denominator later. Okay. Now, is there another obvious value of x that we can substitute into this big old basic equation that will kill off a couple of terms? Anybody see it?
1.
Good. So if I substitute 1 in my basic equation, I'll kill off the A term. I will not kill off the B term. He's still there. But the last term will be 0. Oh, wonderful. So this allows me to get my B. So what do I have? I have 2 minus 4 minus 8 is equal to B times 1 times 5. Do some arithmetic here, and this is where a lot of mistakes can occur, of course. I think the left-hand side is negative 10, and then this is 5B. And if I solve for B, I get B equals negative 2. Save that for later, because he's going to be the guy that's going to be the numerator for the x minus 1 denominator. Okay, fine. Now what? Well, I'm out of ideas. Like, I don't have any values of x that I could substitute now that will kill off any of the terms. So this is the part where you have to be good at algebra. Okay? We do know what A and B are, but we need to get C and D. Those are 2 unknowns we still have to pick up, and you don't guess. You got to get it analytically. So I'm going to use the 2 equation, 2 unknown linear system technique right now. Watch closely how I do this. I've seen books do this, and they do such a bad job of it, and I'm doing this in slow motion for you, and yes, you're welcome. So the idea is you're going to substitute A equals 2, because you have that in hand, and you're going to substitute B equals negative 2 in the basic equation, but you're also going to pick 2 different values for x that you haven't used up yet to get 2 separate equations with C and D in it. And then those are your 2 unknowns. You know, 2 equations and 2 unknowns. So here's, let me do it in super slow motion. I'm going to pick a value of x I haven't used yet. Let's let x equal negative 1. And we already know that A is 2. We have that in hand. Good news. And we have B equals negative 2. So if I substitute those 3 things into my basic equation, I'm going to get this. When I square negative 1, it's a 1. That's why I have that. And now the second term here is bx, x squared plus 4. So b we already know is negative 2. And we're plugging in x is negative 1. And then when you square negative 1, it's a positive 1. So we have 1 plus 4. Plus, and then we're going to have cx, but that's c times negative 1 plus d, parentheses, times x, that's negative 1. Times, and if you look at what that is, it's x minus 1, but we're substituting negative 1 here for x, negative 1 minus 1. So clean this mess up. This is going to take some time, but this is going to be an equation where C and D are unknown. So if I do the math here slowly, I'm going to have negative 2 minus a minus 4 minus 8 equals 8 times negative 2 times 5 plus positive 2 times 5 plus, and then here I still have negative c plus d, and then this number right here, what is that? That's going to be negative 1 times negative 2, which is a positive 2 out there, and then I'm going to distribute this 2 over the sum, so I have negative 2c plus 2d, like that. Now I know this is a big mess, but cleaning it up, I'm going to have negative 6 on the left, that's equal to, this looks like negative, what the heck? Did I screw up? Yeah, this is, sorry, I screwed up. This is supposed to be a 2. Nobody said anything. You guys are asleep also. A is 2, sorry. So this is going to be negative 20 plus 10 minus 2c plus 2d. Okay, now cleaning this equation up even more because it's a mess. I'm going to get the c's and d's on the left and everything else on the right. Are you guys still with me?
Yep.
Okay, good.
Yes.
Yes.
Yeah, this is a nightmare, but you know, this is where it's like, oh man, you're kidding me. If I add 10 to both sides, I'll get a 4 here. And I still have negative 2c plus 2d. I could leave it, but how about if I multiply both sides by a half? So whatever you do to one side, as long as you do to the other, you're good. So if I multiply this side by a half and this side by a half and distribute the half, I'll get 2 is equal to negative c plus d. I'm going to save that for later. Really? Yeah. Then what? Oh, I need another page. Oh, crap. So what do I have so far? I have a negative c plus d equals 2, and I'm saving that for later. Well, now what? Well, you're still trying to get c and d. Wow, this problem is taking a long time, and I'm really getting bored. Yeah, well, too bad. Suck it up, Buttercup. You're not done. So now what I need to do is I need to get another equation that has c's and d's in it, because then I'll have a linear system. So I'm going to still have a be 2 and b be negative 2. But let's pick a different value for x that we have not used up yet. And in my notes, I picked something easy. I let x be 2. We haven't used that up yet. And a is still 2 and b is still negative 2. So I'm going to substitute all of these things into my basic equation. So I'm going to have 2 times 2 cubed minus 4 times x, which is 2, minus 8 is equal to a, but that's 2. 2 minus 1, 2 squared plus 4. Plus b is negative 2, and you're multiplying by x, but x is 2, and then 2 squared plus 4, plus cx plus d, but x is 2, so you'll have c times 2 plus d, and then you'll have times x, which is 2, and then you'll have x minus 1, but that's 2 minus 1. So this big old equation, which is a nightmare, I know. Now what? So on the left, you have 2 times 8 minus 8, that adds up to 0, minus 8, you still have that 8, is equal to 2 times 1 times 4 plus 4, which is 8, plus negative 2 times 2 is negative 4, and then 2 squared plus 4 is another 8, plus, and then this right here is just a 2, and if you distribute your 2 over this sum, 2 times 2c is 4c, and 2 times d is just 2d. I know, this is a nightmare. And so what do I have? I have negative 8 is equal to 16 plus, negative 32, nice, plus 4c plus 2d. Oh, this is just, yikes. But this is negative 16. How about if we add 16 to both sides to move him over, and we'll have, let's see here, 8.
Professor.
16, yeah, there's something.
The
Yeah, over here. Sorry, I screwed up. This is 16.
times 8 is 16.
Yeah, this should be 0. Gotcha. Thank you.
Yeah, 0.
Yeah, this should be 0. My bad. So now we're going to add 16 to both sides. So we should get 16 over here. And now we still have 4c plus 2d. And you could leave it like that, but how about if I multiply both sides of this equation by a half? Just to reduce it just a little so it's not as terrible. Okay, now you're going to save that. So now what do we have? So those of you that are still with me, if you still haven't passed out from, pure tedium, this equation here that I said save, and this equation down here that I also said save is a 2-equation, 2 unknown linear system. So let me rewrite those 2 equations right here, right underneath each other. So you could see that this is a Math 45 problem. This is Math 45. This is a 2-equation, 2 unknown linear system. And you, by golly, you better know how to solve those. Like if you go, oh, I forgot. Well, let me just remind you, there's a couple methods to do it that you might have learned. One is elimination or substitution. One of those possibilities. So it's up to you which one you want to do. How about if I add, or how about if I subtract the bottom equation from the top equation? So if I go negative c minus 2c is negative 3c, and then d minus d is 0, and then 2 minus 8 is negative 6, that's called the process of elimination. And if I solve this for c, woo, I now have one of my unknowns. Hallelujah. And then you can substitute this back into either one of the original equations to get d. So you'll have negative 2 plus d is equal to 2. And if you add 2 to both sides, you get D is 4. Fantastic. Now I'm ready for the calculus. What do I mean? You're going to integrate your partial fractions. So you have A over X, but A was 2. We got that a long time ago. And then you had B, which was negative 2 over X minus 1. And then you had C times X plus D all over the irreducible quadratic that was a sum of squares, okay? Everybody with me? So this is the log rule, this one's the log rule, this is going to require some work. So let's just do the first 2 terms, 2 ln absolute value of x. If you use some u sub here for the second term, you'll just end up with minus 2 ln absolute value of x minus 1. But what are you going to do for this guy? How are you going to integrate that? You're going to split them up into 2 fractions and individually integrate these 2 guys. And you do have enough ammo to integrate these 2 guys. Yeah. Let's see if you guys either watch my video so you know what to do, or maybe you remember. So what rule? Don't say U sub, because U sub is not a rule. Yes, I'm going to use U sub in about 2 seconds. But what's the rule that I need to integrate that term right there? I'll give you some choices. Power rule, log rule, arctan rule, exponential rule, sine rule, cosine rule, what?
Arctan.
Power.
It's a log rule, right?
That's the log rule right there, people. Because you're going to let u be the denominator, and du is 2x dx, so the intermediate step looks like 1 over u du. That's the log rule. ln absolute value of u, and then for us that's ln absolute value of x squared plus 4. You can safely drop the absolute value because x squared plus 4 is guaranteed to be positive, or you can leave it, that's fine. And don't forget, you still have these you still have those logs there. So you still have 2 ln x minus 2 ln. You still have these logs. Now, what about this thing here?
Arctan.
That one is arctan rule. Can you see it?
Yeah.
Okay. So this one's arctan rule, and when you use the arctan rule in Professor Rasky's class, and if you want full credit, you're going to go, what's u, du, and a? I want to see all 3. Tell me on your paper. I want to see all 3. So what's the u here?
X.
X,
Good.
X.
What's the u?
1 dx.
dx,
And what's a?
2.
2.
2. So when you use your arctan rule, remember it's 1 over a, which for us is 1 over 2, arctan of u over a, which for us is x over 2, plus c. And we're done, although they may ask you to clean up all of these logs. So if they do, this is what you would do. You would first start condensing by taking those coefficients and putting them as powers.
4 for arctan.
Yeah, isn't it supposed to be 2
4.
arctan?
Yeah,
Arctan.
sorry, I forgot my 4. Yes, I want a 4 over 2, so that reduces to 2. Thank you. If I condense these 2 guys as a single log, that is where I take the log of the difference. But then I have this log here. And so if I condense these logs together, because now that's adding 2 logarithms together, I'm going to get this. One big old log like this, which is kind of cool. Woo! And then plus my 2 arctan x over 2 plus c. Woo! Okay, that took a lot of work to do that problem. But after you're done, if you get it right, of course, then you feel like you're, Olympic athlete going for the gold. Okay, but you see there's a lot of room for error. Like even I made some mistakes up here arithmetic-wise. So I do give you partial credit. My math lab typically doesn't. Like they'll even give you 0 points if you forget a plus C, even if you did all the work, which is really frustrating. But I'll come in there and I'll swing in and I only take off 1 point if you forget to put the plus C, okay? So what's the recap on this? The recap is a few things. First of all, know how to identify an irreducible quadratic factor. And know that when you make the partial fraction that goes with that guy, his numerator is a linear factor. So you have two unknowns, not just one extra to go figure out. When you have a big old basic equation like this, you can use some easy values of x to get a couple of your unknowns, but you may have to struggle a little bit and figure out to get your two unknowns for getting other unknowns. But I want to tell you full disclosure, I never use this technique, but I wanted you to see it, especially because the this approach may be what when you click on the view an example button. But I don't. I use equate the coefficients technique, which is what I teach all my differential equation students. So I'm going to do this next problem, and this is going to introduce a few things, equate coefficients technique. And for those of you who've never seen this, who are interested and open to learning new things, welcome, because this is an awesome technique, and it's a lot less work than trying to do the two unknowns linear system technique. That can be a little bit more, I'm not saying this is a cakewalk, but a lot of times it's a way less work. So check it out. First of all, I'm giving you a really hard denominator to factor. This is a cubic, and you can't factor it using the diamond method because that won't work. This is a third degree polynomial. So if you recall the rational roots theorem, which says think of all the different ways of factoring the constant term and divide it by all the different ways of factoring the lead coefficient, and then put all those possibilities together, if this does have a rational root, it would be one of these numbers. It's not a guarantee that you'll have a rational root, but it's really nice. So it turns out that x equals 2 over 1, which is 2, is a root of this polynomial. So what does that mean? If you plug in 2, it goes to 0. 2 cubed minus 2 times 2 minus 4 is equal to 0. Check. So what does that mean? It means that x minus 2 is a factor of that polynomial. And now you got to use polynomial long division. Not because this is an improper fraction, but because you're still trying to factor the third degree polynomial. So that's why. Unless you can see it right off the bat, and I certainly can't. So polynomial long division is your friend. And when I teach differential equations, oh boy, I mean, you're going to see all this stuff. Like you have to use your rational roots theorem to help you factor some like third degree polynomials, fourth degree, fifth degree. Oh my God. And you should have learned it in pre-calc. And if you didn't, I'm sorry. So how many times does x go in x cubed?
X squared.
And then you multiply that with your divisor and subtract. This minus this is 0. This minus a minus 2x squared is positive 2x squared. Keep on going. Look at the highest power terms and keep on going. X times 2x gives me 2x squared. So now multiply 2x with your divisor and then subtract. I get 2x again here, bring down the minus 4. X goes into 2x twice, and it's going to turn out you get a 0 remainder, and you better, because x minus 2 is supposed to go in evenly. So now what? Here's the claim. X minus 2 times x squared plus 2x plus 2 is equal to the denominator. Is it factored completely, though? Or can we factor it more? Like, does this factor further? Over the set of integers, of course.
No.
No. This is another irreducible quadratic, I'm sorry to tell you. It does not factor anymore. Bummer. So then what? Well, then you got to worry about your partial fractions. How many and what are they going to look like? So this one is going to have 2. The first one is just for the linear factor of x minus 2. And the second one is going to be the irreducible quadratics partial fraction. And there's your, that's your mess right there. So I'm going to show you the coefficients technique. So now we're going to get the basic equation. How? Multiply both sides by the LCD, which is this guy right here. Once you multiply both sides by that LCD and you clean it up, you're going to get your basic equation. Okay, there's your basic equation. Now, remember, I'll get you 1 point of partial credit if you get that far. So is there a value of x that you can see that if you plug in here, you'll kill off a term or two here? What do you think?
If you do 2, maybe you can find A.
Mm-hmm. Okay, I'm backing up a bit. I see somebody on the chat, Kobe and Jose. Why does it get a C and a D? Are you gentlemen talking about this problem right here?
No, it was for the previous. So like I can ask the same questions. How did you get the CX and the BX plus C for this one?
Well, anytime you have an irreducible quadratic, those guys don't just get a single unknown for their numerator. Irreducible quadratics are very special, and their numerator can't just be like a plain old C.
All right.
Hello? You're going to have to buy this. Just say, okay.
Yeah. And
Just
so
say, I buy it.
So why did you choose BX plus C? Like,
well, what are your favorite letters, Kobe? I can't use A again because A is already used.
So why do you only have only those last two? Like for the other one, how did you get A plus B? Then you got the CX plus D. Why did you use?
Well, okay, the other problem though, Kobe, was different. Let's go back to the other problem. You're getting very confused now, I can tell. And I'm sorry to hear that. Okay? So I'm going back to the other problem right now, way back here. So the reason, ooh, shoot, man, sorry. I went too far and my Surface Pro is not going to let me. So Kobe, in this last problem, can you see my screen okay?
Mm-hmm.
Okay. Do you notice that we had two linear factors, like we had an x and an x minus 1?
Oh, yeah, I got it.
So the x, he needed his own personal partial fraction, and so he had an unknown of a. And then the x minus 1, well, he's another linear factor, and so he needed his own personal partial fraction.
Oh, yeah, I got it now.
And then the irreducible quadratic, that would be a sum of squares, which does not factor. That has the very special numerator that has two unknowns in it.
Yep.
Does this help?
Yeah, I got it now.
So if you're trying to compare this problem to the problem that we're kind of in the middle of right now, they're not exactly the same. Like this problem we're in the middle of right now, Kobe, has one linear factor. That would be x minus 2. So that gets his own personal unknown right there, right?
Yep.
And then he has that yucky irreducible quadratic that gets that weird numerator, in this case, bx plus c. Does that help?
Yeah.
Okay, now back to the basic equation. I'm going to let x equal 2. And when I substitute x equal 2 everywhere that I see an x in this big old basic equation, this term is going to go to 0 because 2 minus 2 is 0. So it's big fat 0 here. And my Surface Pro is really giving me a hard time right now. And I just wish I could throw it against the wall. Shoot, it's too bad. Okay, so now where am I? Well, it's a hot mess. So on the left, I have 6 plus 4 is equal to a times some big old number here. What do I have here? 4 plus 4 plus 2. Oh, that's not too bad. 10 is equal to a times 10. Ah, nice. A is equal to 1. Does that always happen? Oh, hell no. Now what? Well, there's a couple ways to go about this. If you want, you can do that technique where you pick two different values for x, and a is a 1, of course, and you get two different equations with two unknowns, b and c. That will work. I hate that way. I'm going to show you my personal favorite way. Listen up. It's called the equate coefficients technique. On the right-hand side, multiply everybody out. So you may have to do a lot of FOIL. Oops, that's a plus sign and an equal sign. My apologies. Come on, Microsoft Surface Pro. Please stop bugging me. And when you FOIL this mess out, you get bx times x, which is bx squared, bx times negative 2, which is negative 2bx, c times x, that's cx, and c times negative 2, which is negative 2c. Now on the left-hand side, remember this is a basic equation, you have this. Now here's how it works. The polynomial on the left has to be equal to the polynomial on the right. So on the right-hand side, if I collect like terms, like if I collect the x squared terms, and then if I collect the x to the first power terms, I'll put squares around those. Those guys have a common factor of x. So those coefficients will be 2a minus 2b plus c. And if I collect all of the constant terms, so who are the constants? This is supposed to be 2a, sorry. I have 2a minus, really annoying, minus 2c. So this is the constant term. So the polynomial on the left has to equal the polynomial on the right. I hope you're following with me right now because I'm training you in something that I claim is extremely valuable. If you care about really learning, I'm talking to you, people that care. So let's look at x squared terms. This is where you equate the coefficients. I don't even see an x squared term on the left-hand polynomial. Do you? That's true, we don't. So what would his coefficient be? 0, because there is none. But that has to equal the coefficient for the x squared term on the right side polynomial, which is a plus b. But good news, I already know what a is because I got him already. Oh, cool. So what does that mean? If a is equal to 1, doesn't that mean that I could easily get b? What is b?
-1.
Bingo! I just got one of my unknowns, and I didn't have to solve a 2-equation, 2-unknown system. But I still have to get c, so bummer. Now what? Well, there's a couple things. You could either equate the x to the 1 power, or you could equate constants. I'm going to equate the constant term because that's going to be quick. So let's skip. I mean, you can do all. But let's look at the constant. The constant term on the left-hand polynomial is a 4. The constant term on the right-hand side polynomial, I can't even talk, polynomial is 2a minus 2c. But good news, a is equal to 1. So 4 is equal to 2 times 1 minus 2c, and now you can go get your c pretty easily. If I subtract 2 from both sides, 2 is equal to negative 2c, and I divide both sides by negative 2, and I have my c. So beautiful. So now the calculus begins. Well, what do you mean? I'm going to have my a, which I got as a 1, all over x minus 2, plus the bx plus c, all over that irreducible quadratic. And now what? Well, this is easy because you're just going to use the log rule. You know, u is x minus 2, du is dx, and this just looks like, 1 over u du, and you're going to have ln of u, and that's just going to be ln absolute value of x minus 2. Okay, fine. Plus, now, what about this beast? How are you going to integrate that guy? I got my dx. This is a little bit tricky, but I claim that actually the log rule is going to work. This is kind of rare. So if I factor out a -1 from the numerator, if you would allow me, you'll probably see that this is going to be a log rule in a moment. And I'll pull that -1 out front just because it's bothering me. Watch closely how this is going to be the log rule. If I let u be the entire denominator, x squared plus 2x plus 2, then du is what? What's the derivative of x squared plus 2x plus 2? Quick.
2x plus 2.
2 dx.
2x plus 2 dx. Well, that doesn't help. Well, yeah, it does, because if you clean up this du just a little bit by factoring, I usually don't like factoring out stuff, but notice that x plus 1 dx is already in the integrand, and the only thing we're missing is a multiple of 2, and multiples are easy to take care of. So now this integral looks like negative a half, integral of du over u, but that's just going to be negative a half ln of u. And so now we can finish off the problem by back substituting. Oops, that's a minus a half ln absolute value of x squared plus 2x plus 2 plus c. Now this x squared plus 2x plus 2, you can even graph it. It never goes negative, so you can safely put parentheses instead. So that's okay. And then even then, I'll even go one step further. I'll try to rewrite this as a single logarithm just for kicks and giggles. You can do this. You can put all these guys together into a single thing. This is like the square root of x squared plus 2x plus 2 plus c, and we're done with that problem. Woo! Boy, that took a while. So, I mean, that's another one of these crazy partial fraction decomp, but the equate coefficients technique is really nice because it gives you a way to get your unknowns a little bit more quickly by just acknowledging that the left-hand polynomial has to equal the right-hand polynomial after you multiply everything out, and then equate the coefficients for your terms, okay? So any questions on this one? I know this is pretty crazy.
I have a question that you answer.
Sure.
Do you need an absolute value for the numerator?
A lot of times they'll drop it just because they'll sort of assume that you'll be okay with not putting in any values that aren't in the domain of your log.
Okay.
I do want to say something about notation. I've seen some of you do stuff like this, which is really, I take away a point when I see this. I see people do this, ln of parentheses absolute value of x plus 1, something like this, where you do parentheses and absolute value for your argument. This is just not conventional notation, and I've been seeing it since the beginning of the semester, and I try to catch when I see that, and I take away a point every time I see you do that. My math lab lets you do it. I don't like it. So when I see it, I take away a point. So again, you may think that I'm being a little bit strict, and I'll just say I agree with you. And I want my Calc 2 people, when they're done with this class, to be on point with their notation. That's my goal for you. So when you go to your Calc 3 professor, whoever that might be me, I'm teaching Calc 3 next semester, I'll see you there, or whatever other classes you may be going to, like your differential equations or linear algebra, that you're going to be impressing your teacher with good notation. That's the goal, because when you have good notation, it shows that you had a good education, okay? So I'm going to do one more just because I can. Let's do repeated quadratics, and then I'm going to call it a day, okay? If you're still alive, let's take a look-see at this, okay? Hey, you know what? Better yet, I'll save that for next time. Let's go to something else. Let's do letter H, and I'll do the other one next time. This one is kind of weird because there's two ways to treat it. Patrick JMT, here I come, Jonathan. Well, Jonathan, let me ask you a question. I'm talking to Jonathan, my maestre. Did you watch my videos yet? I'm looking in the chat box. Jonathan? Oh, I don't know if Patrick JMT teaches equating coefficients though. Are you saying that you still have a problem with it? I'm looking in the chat box. Okay, then Jonathan, I'm going to do this problem for you. Forget it. Let's go back to this. Okay, Jonathan, before you leave here, I want you to get it. We'll do letter G. Okay, first off, how do you factor this denominator? You learned how to do this in an algebra class. Why? Because I know you did. I taught algebra. I know what the deal is. This is a 4th degree trinomial that's missing the cube term and the x to the 1 power term, and it's actually factorable. And you do it by, you can kind of think of it as u sub, but you know, it's not really that, where you let u be x squared, and then if you square both sides, you replace x to the 4th with u squared. So what I mean is, and here's some scratch here, is this polynomial x to the 4th plus 4x squared plus 4, if you rewrite it where you replace x squared with u, and you replace x to the 4th with u squared, now it's an easy 2nd degree polynomial that you probably can factor upon inspection. And then back substitute. What was our u in the first place? It was x squared. So what I'm saying is that the denominator, if you factor it over the set of integers, is a repeated irreducible quadratic. Oh yeah, and we're going to go late today. Just think of it as free education. You're blessed. You got me as an instructor. You're in good hands here. I'm helping you out. So what am I saying? We're trying to get to the basic equation, but not yet. We're going to have 2 partial fractions. The first partial fraction, ax plus b over x squared plus 2. And because this is repeated, because of the quantity getting squared, you're going to have 2 more unknowns, cx plus d, where the denominator is x squared plus 2, the quantity squared. Oh my God. Now what? Clear fractions. Multiply both sides by the LCD, which is x squared plus 2, the quantity squared, and then clean it up. I'm really blowing this. Come on. Okay. So this is my basic equation right here. I'll give you 1 point if you make it that far. Yay. Now go get 4 unknowns. I need you to go get A, B, C, and D. Well, shoot, man, there's no value of x that I could plug in here that would get me anything. It's like I'm stuck. And this is where, when I put this on an exam last semester, or was it, I think it was last semester, and I also put it on last fall when I taught this class. Woo, boy, half the class missed it because they don't want to learn equate coefficients technique. Yeah, it's just too bad. If you're not open to learning, I'm sorry. And it's really easy, so watch closely how I do this. So the left-hand side is still this weird polynomial, 8x cubed plus 13x. And now I'm going to FOIL, so I'm of ax times x squared, that's ax cubed. Ax times 2, okay, that's 2ax. B times x squared, well, that's just bx squared. Plus b times 2, well, that's 2b. And then I still have cx plus d. Okay, let's make the right-hand side polynomial look a little more pretty by combining like terms, if there are any, because there aren't that many. Like, how many cubed terms are there? Just the 1, so just copy him down. And we'll write in descending powers of the variable. Okay, how many x squared terms do we have? Just the 1, okay. How about x to the 1 power? Now we do have 2 of those. So we'll combine those and we'll factor out the x to the 1 power. And then what about the constant terms? Well, we just have 2 of those guys, and so this together is your constant. Okay, now it's time to equate coefficients, people. And this is awesome. I think you'll get it after you see the second example. Jonathan, I'm talking to you. This is for you. This is in your honor. Okay. So the left-hand side polynomial had better be equal to the right-hand side polynomial. We need that to be true. So let's equate x cubed coefficients together. So the coefficient of the x cubed term on the left is 8. The coefficient of the right-hand side x cubed term is what?
A.
A. Boom, we're done. We just got the A. 1 down and 3 to go because we still have to get B, C, and D. Let's keep going. How about x squared terms? Let's now focus on x squared terms. Well, there isn't an x squared term on the left-hand side polynomial. I know. So his coefficient is what?
0.
Yeah. Thank you. And that had better be equal to the coefficient of the x squared on the right-hand side polynomial, which is B. And B is equal to 0. Oh, tears. Can you have one of the unknowns be 0? Not only yes, but hell yes. It can happen. And it's happening right now. B is 0. Woo! Keep going. How about x to the 1 power terms? Well, on the left-hand side polynomial, the coefficient of the x to the 1 power is a 13. Okay. So what is the coefficient of the x to the 1 power on the right?
2a plus
2a plus c. But good news, I already got a. So substitute in that value for a because you got him already. Let him help you out. Then what? Well, good news. I'm able to figure out what c is. Yes? And c is?
-3.
Boom! Now I only have one guy left. Fantastic. So now let's look at constant terms. Well, on the left-hand side polynomial, there is no constant term, which means he is a big fat 0. And on the right-hand side, you have 2b plus d. But wait a minute. Didn't I already get b? What was b?
0.
Yes, indeedy. So substitute a 0 in place of b, and now solve this for d. But wait a minute. That means d is also equal to...
Zero.
0. Can that happen? Not only yes, but hell yes, it can happen. Well, now what? Well, we have A and C, and if you go back to your original partial fraction breakdown, where the B is 0, and also the D ended up being 0, oh, bummer. So you only had to worry about the A and the C, so now the calculus part takes into account. So here's where calculus actually gets involved in the whole entire problem. Geez Louise, man. So you have AX, but what did we get for A again?
8.
8. So you have 8x over x squared plus 2 plus cx plus d, but remember d was also 0, but c was -3, and this guy's denominator was x squared plus 2 squared. And now you have to worry about, do you know how to integrate? Because this is where the calculus now takes place. So this first term is the log rule with u sub. So u is the denominator x squared plus 2, du is 2x dx. So you can add a 2 and divide 1 out. And this 8, I'm just going to pull it out of the original problem. So now this looks like 8 over a half, or 8 over 2, and then 1 over u du. And I'm having problems with low surface. And so I'm just going to continue on this page. And so this is going to look like 4 ln u, but then you put your u back in, and x squared plus 2 is always going to be something positive. So I'll just drop the bars. Now this thing here is not the log rule. This is the power rule, folks. And so I want to see u is equal to x squared plus 2. du is 2x dx. So you need to put a 2 in there, of course. And while you're doing that, so that's going to really be a half out in front, you will have a -3 constant multiple. And so this looks like du over u squared. But then you know this is really the integral of u to the -2. And that's going to be u to the -1 over -1. And then a negative times a negative is really a positive. And then your u is going to be downstairs. And I'll put him back in. That's x squared plus 2. Plus c, and you still have this log term as the first guy. And I think your final answer looks like this mess right here, and you're done. So that one was an interesting problem because you had repeated irreducible quadratics, and you got to see the equate coefficients technique in action, and it's really helpful, so learn it. I'm done. See you later. Goodbye. I'm going to stop the recording. If you want to hang out for a few extra